Hello, this is the video submission for MSc 491, Machine Learning in Mechatronics Applications. We are Group 24, Mahmoud Kamiladin and Andre Divina Gracia. Our project is a road object detection model performance comparison, where we focus on testing various object detection models for autonomous vehicle applications. As members of SSVU's Formula SAE Club, our team noticed there's a bigger push for driverless vehicles in the FSAE competition. We saw this project as an opportunity to begin on the development of the AI branch of the club's race car. Between different features that go into an autonomous vehicle, object detection is a core building block in its control system. Our objective is to implement a model on an embedded system using a camera for real-time processing. In this project, we aim to compare different models on different embedded systems and determine the best performing setup for an electric race vehicle. The models we are highlighting is You Only Look Once, YOLO, and faster region-based convolutional neural network, RCNN, or faster RCNN. We are running these models on two embedded systems, the Raspberry Pi 4 and the NVIDIA Jetson Nano. There are different training and development pipelines for each framework, API, and architecture. Each of our model is trained with different frameworks. However, they all follow the same general structure outlined in the figure on the right, the bottom right of the methodology. We are using the Berkeley Deep Drive dataset, the largest open driving video dataset with 100K images and 10 classes to evaluate autonomous driving models. It contains the images and the bounding box information for the training and validation set. Each framework requires a different format so that the API can properly interact with the data and the inference information. The frameworks that we are using are Detectron2, PyTorch, and Darknet. Once we generate the trained model, we run them on our embedded systems, a Raspberry Pi 4 and an NVIDIA Jetson Nano. For twice the cost, the Jetson Nano has a dedicated GPU for machine learning applications and has further optimization options to further improve the performance of the model. NVIDIA provides an interface with a GPU called TensorRT that allows the definition of neural network layers in a more computationally efficient manner that can leverage the power of the Jetson Nano platform.
And then for our results in comparison, we had two major metrics that we were comparing the models by. Mean average precision, which is a measure of how many true positives are compared to the true positives and false positives the model generates for each specific object that it's detecting. And the other metric that we were using was frame rate per second in order to compare these models for our goal of deploying it on an embedded system to perform real-time object detection as part of a software stack for an autonomous car. And so as outlined by Andre, the two main architectures that we looked at were faster RCNN and YOLO. And for YOLO, there were many different variations that vary slightly in their architectures and applications. Faster RCNN was the slowest model, which was the expected result as it performs object detection in 2 stages instead of 1 as done in YOLO. But an interesting fact is that even though it was the slowest, it was not the most accurate model, which was YOLO V5S, which had around a 20% higher accuracy with a much faster speed. But then in terms of our requirements, we were looking for something that could balance accuracy with inference speed. And so YOLO V4 Tiny performed well without optimization, running at 14.1 frames per second. But then upon further optimization of quantizing the model and using the TensorRT framework that NVIDIA provides, we were able to get it up to 41.3 frames per second with a mean average precision of 0.2539, which is respectable when compared to the other models that we looked at. And so in conclusion, These models were tested on the Raspberry Pi, and it was too slow for real-time inference, and so the Jetson Nano was selected as the platform of choice, having been twice as expensive as the Raspberry Pi, but performing up to 130 times faster inference rate. And YOLO V4 Tiny that was quantized to 16-bit floats was the best model. And overall, we were able to see the power of the YOLO algorithm in comparison to other other models that are used, such as faster RCNN, and how even though it is done in a single stage, it can still provide comparable accuracy at a much faster speed. And now we will show our demonstration video.
Here we see that different models inferring the classifications of the same video. And for the next video, we run the object detection model on different environments, such as daytime and nighttime.
And then this is me using the Jetson Nano with a camera to do real-time inference. And you can see the camera is pointing at different objects on the road and identifying cars and trucks and people. Thank you for watching our presentation of the poster and the demonstration.